Hi everyone, thank you so much for joining us today for a guest speaker session. We have with us Peter Tong. Peter is a second year PhD student in NYU, advised by Professor Jan LeCun and Signing Z. Peter graduated from UC Berkeley with a triple major in computer science, applied mathematics, and statistics. Today, Peter will be presenting his research work, MetaMorph, Multimodal Understanding and Generation Y Instruction Tuning. Thank you so much for your time, and I'll hand it over to you.
Hi, hi, thank you for the introduction. Yeah, I'm here today to talk about Metamorph, our recent work, multimodal understanding and generation by instruction tuning, and it is a work I've done in my past, with my internship in Meta, and I'd just like to thank all my advisors and collaborators for this, very amazing experience. Okay, so we just started a little bit with the background. So, large language model and multimodal large language model. Like before I could dive into it unified. So the large language models are relatively simple to actually understand. It input language, and then output language algorithms. And what is multimodal large language model? Well, for multimodal large language model, it input language and vision and sometimes more like audio or video or other stuff. And what's usually done is it goes through a modality connector, and it was connected by either directly appended to the LLM or cross attention. But what's very important is that at the end of this, it's still output language as its backbone. So how do I actually go from a LLM to a multimodal LLM here? Well, there are actually two ways of doing it. And the first one, which is what I call a heavy alignment training, where you fine-tune it on more than 1 billion data, usually in image text pairs or interleaved data sets, where there are models like Edifix, Flamingo, or Llama 0.2, where you sort of see that these works have shown in their report or leaked sources that it's require very heavy fine-tuning and usually a very large, gigantic cross-attention model. And there is this other approach, which people are also pretty familiar with, called visual instruction tuning. So what is visual instruction tuning is that they take a pre-trained large language model and then they fine-tune it on less than 10 million datasets. And such works include Llama, Cambrian, Momo, and actually a lot more if you look at the current, the thread of papers. And what's very interesting is that at the end of the days, these two methods actually performance almost equal. So if you take a look at the performance benchmarks of various reports, whether it's newly reported or whether it's previous benchmarks, now you see that at the end of the day, the performance almost equal for these two methods. So the question is, let's say why after 100 times of training the difference that the performance almost equal. So we go back to this magic thing called visual instruction tuning. So from LLM to multimodal LLM, if you train with visual instruction tuning, it means the ability to learn vision is learned through instruction tuning. And in other words, it means it's actually trained with minor visual instruction tuning data, especially comparing to the heavy pre-training stage. And if you take a look at the superficial alignment hypothesis, it says a model's knowledge and capabilities are learned almost entirely during pre-training, while alignment teaches it which steps the distribution of format should be used when interacting with the user. It's actually from the Lima paper. And what does it say here is that the purpose of instruction tuning is an additional alignment stage to trigger whatever is in model's knowledge and capability. But what happens to visual instruction tuning, right? If we see here that visual understanding is something that is triggered from the model with very minor fine-tuning. What about visual generation? And in this work called MetaMorph, we actually show that visual generation is also something that you can trigger from the model if you have proper fine-tuning of training methods. So go into MetaMorph, which introduce something we call predictive visual instruction tuning. So in here, we have is a normal visual instruction tuning pipeline where you have text, you have image, and image is encoded by a either frozen or unfrozen vision backbone. It goes through an adapter, and then both are fed into an autoregressive model, which goes through a text head because you only predict text output at the end. So so the text data here is tokenized into discrete tokens with standard tokenizer used by all LLM training. The vision data here are encoded with a pre-trained vision encoder such as SIGA, and the output is usually continuous visual token. So this is actually a quite important distinction, where the text is discrete and the vision data here is continuous. A common prompt will look like this, where the user might say, what is this image? It display an image, and the model needs to learn to actually predict the text, which says it is a cat. So what is predictive vision instruction tuning? We append an additional vision head on top of this autoregressive model here. And the language head still output a probability distribution over the vocabulary. And it is trained with cross-entropy loss for next token prediction. Whereas if you want to predict the vision here, we use the cosine similarity loss between the LLM predicted vision token and those from a vision encoder here. So an example prompt might look like this, where it say, please generate an image of a cat. And the response here can say, here is the image generated, and then it will generate a bunch of image embedding here. And what if the image embedding are not clear enough? And I want to actually see in the pixel space, not embedding space, but pixel space what happens. So what we propose is we can fine-tune an additional diffusion model with a projector and a diffusion model, and then we'll be able to actually visualize whatever is predicted in embedding space back to the pixel space. So this is an example pipeline of what happens during the inference time, where the model goes through the text, it goes through an encoder, and then during prediction, it goes through a text head that predicts the probability, and which can later be decoded into text tokens and to actual text. And for the vision part here, the model actually predicts a set of embedding. And if we want to look at embedding, we can visualize it through a projector and a diffusion model. But if we don't want to look at it, then it's perfectly okay that we can just leave it in the embedding space autoregressively. And an example conversation looks like the following. Where the model will start to say, can you please generate an image of the animal resulting from a monarch caterpillar's metamorphosis? And
You are muted if you are speaking something.
oh, sorry, I accidentally clicked the thing. Yeah. So an example of the following inference pipeline is we can start with a set of prompt in text. It says, okay, please generate an image of the animal resulting from a monarch caterpillar's metamorphosis. And what model do is model will pick up the prompt and then starting to say, okay, so here is the generated image based on a request with a set of image embeddings in these special tokens. And we want to take a look at what the model actually generated. We use the fine-tuned diffusion model to actually visualize it and project it back to the pixel space, where you can say, okay, it's actually a butterfly, which correctly answered the question here. And you can keep further prompting the model with questions regardless of the diffusion output. You can say, what is the animal in this image? And in here, we'll say, okay, the animal in the image is actually a butterfly. So this is an example of the inference for a trained model here. And we actually train the model on a diverse range of data, ranging from image QA, video QA, pure video generation, visual thinking, and image to image. So image QA and video QA are just the standard VQA or image QA bench dataset that people use when they actually train a visual instruction tuning model. The pure video here are actual score to see if the model can predict the future frames, and the generation data are just what we use to train generation, and the visual thinking and image to image are basically trying to incorporate vision as a part of the response. And before I actually dive into the actual model, we believe, because it's currently relatively a new field, I want to carefully study some of the findings around unlocking this, visual generation ability, because it is something that the model didn't possess before. So here are the questions we're going to ask and study in this work. We try to see, can visual generation be unlocked through lightweight tuning, or does it require heavy and extensive data? Because usually, training a tight T2I model is very, very expensive. The second point is, are visual understanding and generation mutually beneficial, or something that orthogonal that might fight with each other? And the third question is, how much does visual understanding or generation data contribute to understanding and generation ability? And finally, what visual understanding tasks correlate the most with generation performances here? So let's start with answering the first question, which is, can visual generation be unlocked through lightweight tuning, or does it require extensive data to actually study this problem? The experiment setting we propose is we try to use 1,000, 5,000, 10,000, and all the way up to 5 million of generation data to actually train the text to image ability of the model. And we train the model under two settings. The first setting is we fine-tune our only generation data, where the generation data here. So basically, we only fine-tune it with the generation task. The second setting is jointly train with all the other data we mentioned in the previous slides. So that means it's co-trained or jointly trained with VQA, image QA, video QA, and all other data sets we have mentioned. So in here, we use FID to actually visualize the wellness or the goodness of the learned generation model. And so that's on the y-axis. On the x-axis are the number of generation data in log scale. The green line here is what if we train with only generation data, and the blue line here are what if we jointly train with all other data. So here are what we found. We find that training solely on generation data result in inferior performances. So if we take a look at the green line and the blue line, it's quite obvious that the green line here consistently have a higher FID score, which means that the generation quality is much lower. The second thing we found is that when jointly trained with all other datasets, we unlock generation with very, very few samples. So in here, I actually labeled two quite different or quite unique points. The first one is 5,000 samples. And the second one is 200,000 samples, which, if you think about it, you only need 5,000 samples that you see that the ability definitely grokked or unlocked quite drastically, and for 200,000 samples, the performance stabilizes. So what the plot shows is that if you jointly train with all the other data, you only need 5,000 samples to sort of grok or unlock this generation ability with very few samples. But as we sort of see here, that it's jointly trained with all other data, and there are many data categories we studied before. And the problem is, what kind of data is contributing the most to this, unlocking or grokking ability? So we revisit our experiment here. We use 200K of generation data to actually trigger the generation ability. We jointly train each type of data with, image QA, with video QA, with pure video, with video syncing, and with image to image jointly together. And we sort of plot the performances here. Again, on the x-axis, that the metric. FID score means the lower the better, and for clip score, it's the higher the better. We see here that all categories of data will contribute to the generation ability. And it is indicated by if you go from generation only to generation plus whatever category, or to combine all data together, that the performance continues to improve, lower FID score and higher clip score. Also see that understanding data, which are the image QA and the video QA, is the most effective way to actually grok generation here. So you see the drop in FID and the improvement in clip score is the highest when you co-train with understanding data, which are video QA and image QA. And finally, the question we ask is there any correlation between understanding and generating these visual tokens here? Because we sort of see that understanding data seem to bring the most to actually grok the visual generation ability. So we go back to our findings on, can visual generation be unlocked through lightweight tuning, or does it require extensive data? And the answer is, it is actually something you can unlock throughout training. That doesn't require explicit, very, very heavy fine-tuning. So we move to the next question, which is, are visual understanding and generation something which is mutually beneficial, or something orthogonal? Because it's a problem that people really care about. If these abilities are orthogonal, it means we can't have a model to be unified. But if they're beneficial, then it means we can actually train a model, unified model, that benefit each other. So the experiment we propose here is we still use 200K of data to grok the generation ability, to trigger that T2I ability here. We jointly train with different amounts of VQA data, where we sample 1 million, all the way up to 7 million. From Cambrian 7 million, which is our image QA dataset, to form different levels of vision understanding ability. And in here, the x-axis are the VQA scores, the higher the better, of course. And the y-axis here are the FID scores, the lower the better, and clip score, the higher the better. It's quite obvious from the plot that there is definitely a correlation between the VQA performance and the FID performance. And what we see here is that if we increase the amount of understanding data, it definitely leads to better understanding ability, as evidenced by going from the blue dot to the red dot, that the plot is shifting to the right, which means it's getting a better VQA ability. But at the same time, we also see that the model is also enjoying better generation, even when the generation data and training steps here are actually constant. So what this means is higher VQ score will lead to better generation ability in the setting here. So more VQA score, no more VQA data, not only elevates or improves your understanding ability, they also implicitly improve generation with the amount of data used to train generation being constant. So what about the reverse? We already know more understanding data will improve generation. But what about the reverse? So for the reverse experiment, we do the following. We use 1 million VQA to, again, provide a decent level of understanding ability. We jointly train with different amount of image text data to, study the generation ability, where we sample 200K, 500K, all the way up to 4 million to improve the generation ability of the model. And in here, as you may notice, the axes are actually being reversed. So the axes here are now the generation ability with FID score and clip score. And the y-axis here are the VQA ability. And once again, in this plot, the amount of VQA data is actually being fixed. What's changing is the amount of generation data. And very similar to what we have observed in the previous plots, that more generation data will lead to better generation ability. So going from blue to red, what we observe is that with more generation data, the FID score decreases, which means you have a better FID score. And the clip score increases, which means the image text alignment of the generated images are better. And simultaneously, we also observe that it brings better understanding, or it brings better VQA score, even when the understanding data and the training steps are constant in this case. So we have seen in the previous plots that understanding and generation seem to be something mutually beneficial, but do understanding and generation contribute equally or matter equally when we train a unified model? So we go back to our finding boxes, and we can now answer this question to say they are actually mutually beneficial instead of something orthogonal, which is good news for whoever wants to train a unified model in the future, because it means if you want to pump up your generation ability, you also pump up your VQA score, and vice versa. We now move on to our third point, or third point of study, which is how much does more visual understanding and generation data contribute to understanding and generation? Because we want to find out what is the most effective way to improve both ability. So in order to study this problem, we train 1 million, 4 million, and 7 million VQA data cross or intersect with 200K all the way up to 4 million generation data. So it's basically will provide different level of VQA score and different level of understanding and different level of generation, and we intersect them together. And we measure their average VQA score as well as the FID score and clip score in this case. So the x-axis are if you increase the amount of understanding data. The y-axis are what if you increase the amount of generation data. And the intensity of the color bar means the better performance. So the first thing we notice is that when understanding data is low, it means if we only have 1 million understanding data, then increases in generation data will lead to noticeable improvement here. That we see the color going from white all the way to darker and darker as you have more and more generation data when the level of understanding is quite low. But what if however, if the VQA data scales up, the understanding ability improves here, then what we see is that increases in generation data will contribute minimally as we go from 200K all the way to 4 million. Actually, in all three categories, not only understanding, but also generation. So now we sort of answer this question with that the visual understanding is much more effective comparing to visual generation to actually improve both ability here. And finally, the question we try to study is which visual understanding task correlate the most with generation performances. Because there are so many different types of VQA tasks, like general, OCR, knowledge, etc. So which ones matter the most, or I guess which one correlate the most with triggering your generation ability here? So we cluster our VQA benchmarks into the following categories, which have general, which mean general VQA are just those that ask you a general question. Vision centric, which has the ones that probe into the visual details of an image, like left or right, counting, who's on top of what other or who's under what other. Text and chart, which measures basically model's ability to understand OCR and text data. High resolution, which is model's ability to understand high resolution images. And finally, knowledge, which is basically model's ability to actually um, solve a college exam or solve some very professional questions. So we see at first glance is that general, vision-centric text and chart exhibit very strong correlation between um, these tasks exhibit very strong correlation with generation. So in here we computed the Pearson correlation score between these tasks and generation. And in here, the Pearson correlation are all very high, 0.9 or 0.8, which stands for strongly correlated with understanding. We see that high resolution tasks exhibit quite modest correlation with generation ability here. So the Pearson correlation is still pretty high, it's 0.7, but it is not as high as the other domains we have been seeing in this plot here. And finally, we see that the knowledge tasks seem to be less correlated with generation. So science QA has still a decent 0.6 correlation, while on the other hand, benchmarks like MMMU seem to be almost just uncorrelated with the understanding ability. Um, so what the results here seem to suggest is that visual generation aligns with the visual intensive understanding tasks that people have found in the previous literature. That that it basically showed the visual generation. It seems to be a fundamental vision capability in a large autoregressive model here, as opposed to knowledge, which requires more of the LLM capability.
Hi, I think you are mute again.
Oh, sorry. Um, and and yeah, and so finally, we want to study to see if the findings we sort of have been found were transferred across large language models, because we want to actually just study or raise a finding that's relevant to only one LLM. And here we'll conduct an experiment with 7 million VQA data and 1 million generation data. We train our model on Llama 3 8 billion, Llama 3 8.1 billion, and as large as Llama 3 70 billion. And we'll try to see if our findings still hold in this case.
Hi, Peter. You are mute again.
Sorry, it's very strange. Why it's like automatic muting myself? Um, okay, I hope this doesn't happen. Okay, so basically what we find is that stronger language models will lead to better understanding and better generation score simultaneously. So when we move from lambda 8 billion to 3.18 billion, 70 billion, we see that the VQA score improves and the generation ability also improves with the same set of training data here. And finally, we move on to the section which, after we know some insights in building a unified model, the question the question becomes, why do we want to train a unified model here? And I think, in this world, we think, there are two different um, aspects which we believe favors a unified model. One is, of course, it has a good performance, and number two is it will show ability of, power show ability of modality unification, i.e., it will be able to do some things that a unimodality model cannot do here. So in this slide, we basically show that quantitatively, MetaMorph offers pretty competitive understanding and generation across the benchmarks on image QA, video QA, and generation. And the next slides, I'm going to show some of the more qualitative ones, which seem to show that the large language model, uh, basically, we can leverage the ability of LLM trained with only language here. So the first thing we see is that a fine-tuned unified model can visualize the concepts trained with only text into pretty accurate images. So in here, what we do is we try to probe the model into generating some of the professional terms like chogri, anchila, or view of chitarira, which are some of the very professional terms that is seen in the text-only training, but more long tail when you train a T2I model here. So we compare with Stable Diffusion 0.58 billion as well as JNIS. What we see, for example, when we try to ask it to generate things like Chogri, the second highest mountain in the world, Anchila, a cute cat species in America, and finally Chitarira, a isolated wilderness region in Zimbabwe. What we see is that these, professional models like Stable Diffusion 4.5, although you generate very beautiful images, at the same time, it will also, fail to generate those concepts because, they are more long tail in the normal training distribution. But the LLM, on the other hand, has a pretty decent knowledge of the 2D world, even though it is text-only trained. It actually gets what a Chidorira looks like implicitly, and it has the ability to turn it into accurate visual tokens after visual generation or after this, MetaMorph fine-tuning. At the same time, we sort of observe that the LLM provide better semantic understanding comparing to encoding models here. So regular models uses these text only text encoding encoders like BERT, T5, or CLIP model here to actually encode text into representation. And so again, these are the Stable Diffusion 0.5. And on the other hand, the LLM seems to provide better semantic understanding. So when we ask the questions like a bookshelf with a few books and a bookshelf with many books, the Stable Diffusion 0.5 here will just, generate a lot of books in both cases because, it's pretty hard for the encoding model to grasp those concepts. MetaMorph, on the other hand, because the LLM here provide better semantic understanding that the LLM will actually able to get those differences semantically and generate two settings. One is a few books, and another one is many books. The same applies to this one, which is with versus without, a glass without water versus a glass with water. And in both cases, the stable diffusion 0.5 will just generate very beautiful images, but semantically incorrect, that it contains water in both cases, and MetaMorph here will provide basically better semantic understanding. And finally, things like slightly tall building versus very tall building. Um, Again, the encoding models might fail to encode those concepts, while on the other hand, the LLM-based unified model can very easily capture those semantic nuances. And finally, we see that the model seem to have implicit reasoning abilities. Um, and so this is a slide from the very famous physics of language models done by Alan Zhu or Zhu Zheyan. And what Alan wrote in the paper is that LLM seem to exhibit a level 1 reasoning skill, and it secretly learned a level 2 reasoning skill, which means the model pre-compute um, reasoning graphs before generating any chain of thought tokens. This is what Alan had found in language-only models. And we try to see that if this observation can extend to multimodality case, that the model can pre-compute the reasoning plot graphs before actually entering multimodal generation. So here is the example we give. It's like you can generate an image of the animal resulting from monarch caterpillar's metamorphosis. So these are actually a puzzle if you think about it. They require a few steps of like little reasoning. So you need to actually identify what is a monarch caterpillar, and after go through metamorphosis, it becomes a butterfly. And then you need to understand what a butterfly looks like. So we just give this prompt to Stable Diffusion 0.58 billion. As you can see, it generates pretty beautiful images. It's a caterpillar, but it's wrong, it's not a butterfly. Unfortunately, although it's very good looking, but the model doesn't seem to grasp this understanding here. And if you give the same prompt to MetaMorph, that although the imageries are less beautiful, but we definitely see that the model seems to grasp the correct concept here. And we see that the implicit reasoning skill seems to extend to multimodality here in this case. Here we'll just provide more examples. The first one is the national flag of the country where Yellowstone National Park is located. So in order to answer this question, one would need to identify that Yellowstone National Park is located in America, and then what does an American flag actually look like? And if you compare with solution example, MetaMorph definitely solved this puzzle before generating the token. So it didn't generate anything related to Yellowstone National Park because it did solve the puzzle and realize it's an American flag. The second prompt we give is the flower is celebrated in Spring Festival in the country where sushi is originated. So here, one would need to identify that sushi is originated in Japan, and the flower in Spring Festival in Japan is the sakura flower, and finally, sakura flower looks like that. And once again, the unified model seems to grasp those concepts implicitly. And finally, we'll give a very hard or harder example to the model, which says the large mammal that shares its name with a constellation, often visible in the night sky and associated with the northern part of the world. So this puzzle becomes a little harder because it's like a four-step reasoning. You need to know the constellation associated with the northern sky is called Ursa Major, and Ursa in Latin stands for bear, And then the large mammal named bear is, looks like, the following. And in here, we also observe that the metamorph seem to grasp and to solve this puzzle very well, completing this, implicit four-step reasoning puzzle. So what are some of the takeaways of the work? So this is what I sort of have learned. That one, visual generation is something that can be triggered with visual understanding. It is a skill already possessed by text-only large language model, and we see that LLM may have learned at least a 2D world because after very, very, very minor fine-tuning, the model seemed to grasp how do we generate something visually. It means, again, that this is the ability that the model already possesses and try to just trigger it or unlock it. We see that the visual generation and understanding as something mutually beneficial and synergistic. We see that increasing data on both sides will improve both capabilities. But once again, we see that the visual understanding data are much, much, much more effective. We see that increasing generation data contribute more when the understanding ability is very weak. But when we have a strong visual generation ability, then the contribution of visual generation data becomes much, much more minor. And we also see that visual generation correlates strongly with fundamental vision capabilities, like general, vision-centric, and text-centric. Finally, we see that the advantage of LLM, I guess, our aggressive modeling, will transfer to unimodality or unified model. It provides better text understanding than CLIP and T5 encoding module. At the same time, we observe these implicit reasoning skills will transfer across modality. And thank you very much.
Thanks a lot for the session. I have a question. So, do you have some results regarding if the spatial understanding how spatial generation is improved if spatial understanding of vision is improved?
Yeah. Oh, yes. So here we sort of see that, the spatial understanding, or I guess more broadly, basically semantic understanding, or spatial, like who's on top of, who left, right, field, many. This kind of understanding definitely seem to improve with a language model. And it's actually not only our work, but also if you look at some works like recent ones like Playground V3, or the T2V or text and video models, they're also starting to more and more using LLM as a backbone because it does provide better semantic understanding for the model to actually decode or actually generate visual stuff.
Right, right. Makes sense. You can unmute and ask question if you have.
Hello, thank you for the presentation. So, my question is that does it only support English language? Is there any test have been tested for other languages that if the prompt is in another language, then what would be the results of this thing? And second question is that knowledge tasks are less correlated. What would be the possible more reason that are the model are predicting next visual token? That's why.
Oh, sorry, sir. I didn't actually get the first question. Could you please repeat it again? Sorry.
So my first question was is this only English centric model? Like what would happen if another language prompt would be added?
Oh, so you mean only for English? What about other language, or is this a question?
Yes, yes, yes.
Oh, I see, I see. Yeah. So I guess this really depends on the property of your language model. So if the language model already has a good multilingual understanding, then the ability will transfer. For example, in here, the base model is Llama, and we have a French speaker in the team, and so we also tested with French, and it does perform pretty well. But you know, if this model is undertrained in certain language domains, like for example, we tested Chinese, when we just play around with the model, we definitely see that in areas where the model is undertrained, um, the language undertrained, then the performance is definitely suboptimal.
So if the base model is high centric to the more languages, then the performance would be increased for those languages. That's the hypothesis.
Yes, yes, yes. I guess it really depends on the wellness of the pre-trained language model.
Thank you.
Hello. Uh, was there, did you test it on creating multiple objects like like 4 5 objects with various interrelation between them? Because current diffusion models cannot actually grasp multiple objects uh, and the relations.
Uh, Sorry, I'm sorry again. You sound a little bit far, so it's a little hard to catch the question.
Now, I'm saying, did you test it on multiple objects and the relationship, like 4 5 objects and like defining like for text from like for the image generation task, giving 4 5 objects and the relationship between them. How was it in those aspects?
Oh, I see, I see. So it has with like a few objects, and it does seem to perform pretty well. It's like we sort of view this work as the language model sort of provides a sketch for the diffusion to actually paint, and the language model because it has a better semantic understanding, so it does seem to handle basically how to sketch out the 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 image pretty well, and then it's left to diffusion to actually make it look better in the pixel spaces.
Uh, is there any plan to open source it?
Oh yeah. So because we've done this working Meta, and unfortunately I think we are working pretty hard to open source at least the training code, but for the model itself, we're also trying to open source the model, but I guess the diffusion part is almost impossible to open source given the company policy.
Thank you.
There is a question in chat box as well, if you can have. The question is saying, do you think this approach would work with discrete tokens from something like a VQ gain fed to the model in same way as text tokens?
But yeah, I think it will, but the problem with the VQ is that usually the VQ or the vector quantized embeddings are less discriminated. So I believe the synergy will continue to coexist, but it becomes a research problem of how do we have a good VQ model with very good understanding of it.
I have one more question. So, in fact, two more questions. First question is related to one of the benchmarks that you showed, which showed that when it is when the data set is generation plus image QA, it gives more improvement as compared to when the data set is generation plus video QA.
Yeah.
In general, I think one of the papers I read was which showed that ImageNet is worth one video, which showed that if you generally train on video, the performance is and understanding is more as compared to the image data set. So why in this case image QA gives more improvement as compared to video QA?
Oh, good question. Good question. I believe it's also related to basically the uh what's it called, like the quality of the generation data. Sorry, the understanding data. Because normally, if we train on image QA, it is a more well studied and better curated data set. So it provides better performance here. But if we can have the same level of quality of video QA data set, I believe it also provides the same level of helpfulness.
Right, right. Thanks.
I'm sorry if I missed it, but do you also have image and text alignment scores for this model?
Or even do image text alignment.
Yes.
Oh yeah, so it's like a visual instruction tuning work. So there are two-stage training. One stage is you train the connector with image text data, and another stage is you just do the fine tuning.
One more question that I have is that uh, currently you are generating embeddings and then passing it to a diffusion model. Do you think that it can be extended to like some autoregressive behavior in LLM, that where LLM generates image instead of passing it to a separate diffusion model?
Yeah, I think it's possible. I think it really traces to how do we view this question. So if you want the model to directly generate pixel space, for example, then I believe it's somewhat challenging. But if we keep to generate embeddings, then it's like a diffusion model, for example. Uh, yeah, I see the comment. Actually, for Janus, it's also so it's like diffusion model where you still actually generating embedding, but instead you're generating embedding of a V2 GAN or V2 BAE, and you still need a decoder to actually project it back to the pixel space. So in here, what's similar is that we can also generate the embedding, and then instead of training a diffusion model, we can train a decoder, like a V2 decoder, to actually decode it back to pixel space. But directly generating pixel is somewhat challenging because it's pretty high dimensional, even for diffusion models.
Right, right. And one last question that I had was related to pixel grounding understanding. So, because I think it is also a little bit related to my previous question, because I think if we have something in auto-regressive manner, we can extend it to a lot of vision tasks. But I think diffusion model can also be extended to these pixel grounding tasks where we can segment out or calculate depth as well for. And I think this technique would also help with those tasks as well.
Yeah, I definitely agree. And um, I think like not this work, but some previous work like Momo or QM, I think also show that the language model itself also can be transformed into doing those pixel grounding tasks pretty well.
If we don't have any other question, we can conclude the session here.
Thank you for having me.
Thank you so much for your time. It was really insightful session.